As is usually the case when we go to a new functional group, we start with how we can make that functional group and then move into reactions of that functional group. And we usually start with the functional groups and what reactions we already know. So looking at carboxylic acids, and since we're well into the semester now and well into the year, we know lots of ways to make carboxylic acids. So you know what that means? That means it's time for the online quiz, at least the first part, to be about review reactions. So for your online quiz, question number 1, how would you convert a primary alcohol to a carboxylic acid? For questions number 2 and 3, and remember I'm hand grading this so these are interchangeable, but how would you convert a double bond into a ketone and, more importantly, a carboxylic acid? There's 2 different sets of reagents to do that. How do you take a triple bond and convert it into 2 carboxylic acids is question 4. Question 5, how do you take an alkyl benzene and convert it to benzoic acid? Now, some of these should be easier than others, and we're not done yet. Take a halogen. Now, it's a halogen attached to a cyclohexane ring, but the same thing would be true if this was a benzene ring. How do you convert that to a carboxylic acid? How do you convert a cyanohydrin to an alpha hydroxy carboxylic acid? How do you convert an aldehyde to a carboxylic acid and the reagent would give you a silver mirror? How would you convert an aldehyde to a carboxylic acid and it would give you a brick red precipitate? So there's the first 9 questions for the for the online quiz for this lecture. And stop swearing at the computer. So now let's go on to talk a little bit about carboxylic acids, and I'm going to take at this point and again talk about carboxylic acid derivatives. I did this a few lectures ago, but basically I'm going to start getting into more detail. So here's our carboxylic acid, and a carboxylic acid derivative is going to be a compound where we attach a Y group to the carbonyl. Now, when the Y is a methyl or hydrogen, then that's an aldehyde or a ketone, and we pretty much have talked about all the reactions of those in the previous lectures. If we now put Y groups on here that are different, we get carboxylic acid derivatives. So the carboxylic acid derivatives that we're going to talk about are things like, why did I just write another Y group? Let's get an eraser. Let's start with a chlorine. So one of the carboxylic acids is the carboxylic acid chloride. And we've talked a lot about those, and we'll talk about those in a few minutes. Next, I would introduce a new carboxylic acid called a carboxylic acid anhydride. So all of these are carboxylic acid. This is called the acid anhydride. And in the next coming lectures, I'll talk more about carboxylic acid anhydrides, a little bit how to name them and what their reactions are and how to make them. Today I'm just going to go through carboxylic acid chlorides as the derivatives and finish up carboxylic acid reactions. Then next, I'm just going to put carboxylic acids here and there's a reason for this. Next, let's put an OR group on here. And we know that that is our ester functional group. We know how to make esters, and we know some reactions of esters, Grignards, reductions. We're going to talk more about their mechanisms in the coming lectures as well. And then finally, amides. Just having gotten done with amines, we know a little bit about how to form amides. But these are our carboxylic acid derivatives that I'm going to talk about. And I'm going to group them this way. Every single one of these has this Y group attached to the carbonyl. Now I know here the Y group is an OH, but that's perfectly fine. Now, the way I've ordered these in terms of the Y group being a Cl, in terms of being this, in terms of being OH, in terms of being OR, in terms of being NHR. Now, if I made every one of these a negative charge, what I've just done is I've just ordered these groups in terms of their leaving groupability. A chloride ion is going to be the best leaving group. An N- is going to be the worst leaving group. And so as we go down the line, and this would be a carboxylate, a deprotonated carboxylic acid. It's a little bit worse group than a chloride, but it's better than hydroxide. Hydroxide's better than alkoxide. Alkoxide is better than amide. So I've ordered these Y groups from best leaving group to worst leaving group. And one of the things that we're going to see here, and we actually already have seen, is that these carboxylic acid derivatives then are ranked according to the most reactive now, being the carboxylic acid chlorides, to the least reactive in terms of amides. And you may say, well, most reactive and least reactive in what reaction? Here's the reaction I'm talking about. Take this Y group. We're going to start by adding a nucleophile. I'm going to go ahead and add a negative nucleophile. I'll talk about negative and neutral nucleophiles here in a moment. Our Nu- comes in, attacks that carbonyl. When it attacks that carbonyl, we know that that pair of electrons moves up so that we form a CO-. Now I've got a Y. Now I've got my nucleophile. And what I'm going to talk about is most reactive or least reactive reaction when it comes to the substitution of the Y group with the nucleophile. So in this case, this pair of electrons on the oxygen tries to come back down. And now we're going to have a competition between the Y group leaving or the nucleophile leaving. Of course, if the nucleophile leaves, I go right back to the beginning. If, on the other hand, the Y group leaves, then I would end up forming the carbonyl with now the nucleophile substituted for the Y group. I don't know why the president is coming through on my computer. All right, so that's what happens. So we've got this Y group, and this is then going to be substitution. So this is the reaction I'm talking about. And we can now kind of understand, well, if I'm talking about substitution, of course, if Y is a good leaving group, you're going to have acid chlorides being the most reactive. If the Y group is a lousy leaving group, then that molecule with the Y group substituted here is going to be the least reactive. So this is what we're going to talk about with carboxylic acid derivatives, is their substitution reactions. And if you go back, and I'll remind you of this, we've already seen many of these reactions occur, particularly when the nucleophile was either an R- in the case of a Grignard or a lithium organolithium compound, or an H- if it came from sodium or lithium borohydride. So now let's talk a little bit about, in terms of the carboxylic acid derivatives, how strong nucleophiles attack them. Well, to be honest with you, I just did that mechanism, and we've done this mechanism before. If I react this with a strong negatively charged nucleophile, like R- or H-, and those are the two that we've used the most. The nucleophile comes in, attacks the carbonyl, we end up forming an O-, and when this nucleophile's been R or H, of course, then it doesn't leave, because an alkyl or a hydrogen are not going to leave. So when this pair of electrons comes back down, Y is easily leaves, and so we end up losing Y-, and we end up forming our carbonyl and doing substitution. So that's how the strong nucleophiles will attack a carboxylic acid derivative. And of course, here we could have an equilibrium, because if the nucleophile is a better leaving group, then we're just going to reverse that equilibrium and go right back to the beginning. And in essence, that's what happened when we had a hydroxide and an aldehyde or a ketone. We had this equilibrium occur back and forth. What happens when we do this reaction under acidic? So let's look at how a neutral nucleophile would attack a carbonyl. First of all, we would have our carboxylic acid derivative. If we have a neutral nucleophile, what's going to happen is that it's going to have a hydrogen attached to it. We know that neutral nucleophiles, except maybe amines, are not going to be able to attack the carbonyl directly. So this reaction is going to need some help. And so we're going to use acid, and we're going to protonate that oxygen. And so when we protonate our carbonyl oxygen, we end up with that oxonium ion. And then our, oops, I'm getting ahead of myself. Then our nucleophile will come in and will then add to the carbonyl. So I shouldn't get ahead of myself here. Now my nucleophile is going to come in, attack that carbonyl, pair of electrons goes up here. Again, these are all equilibrium steps, so that I end up with my OH, my Y group, and then my nucleophile with my hydrogen attached, which means that's going to have a positive charge. And then, just to be consistent with what we've done so far this year, we're going to lose H+ to then form this molecule. Now, sometimes there are a couple of mechanisms, or a couple of steps that could occur after this. If this Y group can readily leave on its own, this pair of electrons will move back down here, kick off that Y group, or kick off the nucleophile, depending on which one is a better leaving group. Let's say Y is a better leaving group than the nucleophile was. So we bring this pair of electrons, kick off the Y group. So it is possible that we could lose the H+ and the Y- in this step to then reform the carbonyl with the, oh, I just lost that Y group. And then I would do my substitution. So that's one way this reaction could occur. If Y will not leave on its own, then what will happen is that Y group could then accept the proton. So that Y group would have to have at least a lone pair, so that it became protonated, which we know would make that a better leaving group. And so, wait, wrong. So that this Y group then could leave on its own, so we could again lose the HY molecule. But now what would happen is now I would end up with a carbocation there, which we first saw back in the Pinnacle rearrangement. We would now then regenerate the catalyst by losing H+ to now give us the substitution product. So really the mechanism is going to diverge at this point depending on whether if Y is a good leaving group, we're going to go through this step. So that's if Y minus is a good leaving group. If Y minus isn't, so down here, if Y minus is not a good leaving group, then we're going to have to protonate it and have the reaction occur the rest of the way. So each mechanism is going to be slightly different from this respect, and we'll go through a number of these mechanisms, but this is the basic of how a neutral nucleophile is going to be able to attack a carboxylic acid derivative. It's going to be under acidic conditions, whereas a strong nucleophile, the reaction is just going to occur all at once because it doesn't need the acid's help. So let's go back and look at Fischer esterification then. So for Fischer esterification, we take a carboxylic acid, we react it with an alcohol in the presence of acid as the catalyst. What would the mechanism of this reaction look like? Well, it's been a while since I've said if you're an overly ambitious go-getter student, maybe you would stop the tape and try and write out the mechanism of this reaction using this as kind of a model. So you can try that, stop the tape and see if you're right. If you need one more example to see, or you're not overly ambitious go-getter student, which nobody would want to admit to, we will go ahead and just protonate that carbonyl oxygen, and then we would have our alcohol come in and add to the carbonyl, have this pair of electrons move up here, hopefully you either did this right or you're getting a strong sense of deja vu because I did it on the last slide. But now you would have this oxonium ion, which I would then say, okay, let's go ahead and lose the proton here. Why am I writing it there? I should write it here, minus H plus, and then that would give us now this intermediate, which is not, it's not a hemi, it's hemi nothing because this isn't an aldehyde or a ketone. But now what would happen then is now we would say, okay, let's bring in our acid and let's protonate one of these three groups. Well, if I protonate the OR, I'm going backwards. If I protonate either one of these two OHs, then I'm going to go forwards. And so does it matter which one that you would protonate? Actually, you will probably will protonate both of them equally, but since they're both OHs, it won't matter. So we protonate this one. Now what happens? We lose water, and now I'm down to my carbonyl or my carbocation, and now final step, just go ahead and regenerate the H plus catalyst by moving this pair of electrons to now reform the carbonyl, and there's my ester. So this is the actual mechanism for Fischer esterification, and it is the reason why we have to use H plus. But you could reverse this entire process by simply adding H plus to the carbonyl and then having water attack the carbonyl carbon and have this whole process work backwards. Now, one of the things that you could do in terms of looking at this mechanism, and I'll take a minute here to sort of describe, because if you're curious to say, if both of these OHs are truly identical, is there a way that we could actually tell whether the oxygens are whether these two oxygens are actually switched or which one is lost. And this is where people use isotope labeling experiments to try and to figure out this mechanism. So it turns out that oxygen has an oxygen 18, an oxygen 17, and the oxygen 16 isotopes. Oxygen 18 is radioactive, I believe. Oxygen 17 is very rare. There's only a finite amount of it on the Earth. Oxygen 16 is our major isotope. And so what you can actually do is that if somebody was to prepare, for instance, a carbonyl compound that had an oxygen 18 isotope at this carbonyl, they would then look at their product to see where the oxygen 18 came into play. And what you would find is that in 50% of the molecules, the carbonyl would actually be oxygen 18, which means that this oxygen was the one that was protonated. This oxygen was protonated and then lost, but 50% of the time the O18 would be lost. But one of the things that they never found was this oxygen being oxygen 18 labeled, and so it was absolutely clear that this alcohol came from this oxygen came from the alcohol. And then you could also label this with oxygen 18 and show that in 100% of your product, this oxygen right here would then also be oxygen 18. So people actually have thoroughly studied this mechanism, and using those isotopes is actually how they would do that, either by NMR, looking at the particular isotope of oxygen, or if it's radioactive, they could measure how much radioactivity was in the sample. So that's the mechanism of Fischer esterification. Fischer esterification has a couple of issues. Number one, this reaction is, the disadvantages of using Fischer esterification are it's an equilibrium reaction. And if you've taken lab this semester, if you are looking at the Fischer esterification, you know that in order to push this equilibrium all the way to the right, you have to use an excess of either alcohol or carboxylic acid. And so you actually, you don't have good what's called atom economy. In other words, this reaction isn't particularly green from the standpoint that I'm using a lot of excess reagent instead of a 1-to-1 molar ratio. So the equilibrium is the big problem. That's the disadvantage. Now, one of the alternate ways around this is to do the reaction with an acid chloride. And I'll talk about this mechanism, I suppose, in a few minutes. But we would if we take the acid chloride and react it with an alcohol, I can go ahead and get away with using a 1-to-1 equivalent because this reaction is 100%. There's no equilibrium, so I form my ester, and I would also form HCl in this reaction. Now, of course, I've got to make my acid chloride, so that's an issue. Another way that's been used to convert carboxylic acids into esters is what's called using what's called diazomethane. And so diazomethane turns out to be a fairly easy reaction, although the diazomethane has to be synthesized freshly and kind of in situ, so it's probably not as good as an acid chloride, but it will work. So diazomethane as a compound has the formula CH2N2. So what I'm going to do is I'm going to react my carboxylic acid with CH2N2, and this molecule, this is diazomethane. Now I could ask you, hey, what's the structure of diazomethane? And you'd say, well, how am I supposed to know? And I'd say, diazo, ring a bell? And you might say, well, wasn't the diazo dyes had an N double bonded to an N in them? And so in this case, that must mean that the CH2 is bonded to with an N double bond N in it. And that's true, except that what really happens is that we've got a CH2 double bonded to the N that now has a +1 charge, and the other nitrogen has 2 lone pairs on it, so it has a minus charge. So this is diazomethane. There is another resonance structure form for diazomethane, and that would be to have a negative charge on the CH2. So in other words, move this pair of electrons here, move that pair of electrons there to now form my N triple bond N. So now my negative charge, and this nitrogen is still positive charge, but my negative charge is now on my carbon. And it's actually, well, the true structure is the resonance hybrid, right? But we'll look at the second resonance structure as actually the actual reagent. So here's what happens. What happens is that we end up reacting our carboxylic acid with this resonance structure of diazomethane. What do you think happens in this reaction? Oh, I should make this a quiz. I should make this a online quiz question. How about this C- comes in and deprotonates that carboxylic acid, so that I end up forming the carboxylate and a CH3 now, N triple bond N with a plus charge. Okay, that makes sense, right? It's a C-. Okay, what do you think happens next? Well, this guy right here is a great leaving group. Why is it a great leaving group? Because it will leave as nitrogen gas. So what will happen next is you'll have this O- will attack that carbon, a pair of electrons will go to the nitrogen, and I will end up methylating my carboxylate ion and forming N2, which is a gas that just bubbles out of solution. And hopefully it bubbles out of solution and doesn't, quickly form nitrogen gas that, blows up the round bottom flask, which is always a possibility when you're doing diazomethane reactions. You just have to be very careful. So this is the mechanism for diazomethane. And in this case, we're actually making specifically the methyl ester of a carboxylic acid. And this reaction works fairly well. You do have to synthesize the diazomethane because having a nitrogen gas molecule embedded in it is not a particularly stable reagent, so you have to generate it kind of in situ. And so we actually use this, if you're going to use this, you use this to methylate a carboxylic acid in fairly small scales. And you would really diazomethylate a carboxylic acid if you had another functional group in your carboxylic acid that might not be particularly stable to the thionyl chloride that you would use to make the acid chloride. Or if you were going to do Fischer esterification, of course, you have to use sulfuric or phosphoric acid. Well, if you had another functional group in your molecule, the phosphoric or sulfuric would completely destroy that. And so this is actually used to methylate what are called delicate carboxylic acids. But really only can be used for small scale reactions. So we can make esters by acid chloride alcohol, Fischer esterification of carboxylic acid alcohol, or the diazomethane reaction. Okay, Other reactions of carboxylic acids, because that's what we're talking about now. So you can convert carboxylic acids into esters. So I should probably go back to the beginning here and say that what we're talking about now is taking a carboxylic acid and converting it to an ester. So we've already seen 3 reactions to do that. Now I should take an aside here and say, well, how do we convert a carboxylic acid into a carboxylic acid chloride? If you said SOCl2 or PCl3 or PCl5, you're correct. Next, I want to talk about how to take a carboxylic acid and convert it into an amide. And that's going to require us going back and remembering this reaction from the other lecture. Carboxylic acid reacts with, let's say, an amine. What is the product of this reaction? If you said carboxylate salt, you are correct. So, how does this get converted into an amide? It's a fine question to ask. Well, first of all, in order to do this reaction, what you really need to do is you really need a lot of heat. And so what in essence happens in this reaction is that you're going to heat this up and you're going to lose water to form the amide. So I'm going to lose H2O off of this and form the amide. Now, as far as the mechanism of this reaction goes, where I'm not going to go into it at this point, but this really does require a considerable amount of heat to decompose, and that's what we would call this. We would call this a decomposition of the ammonium carboxylate salt to give us the amide. We've actually, in my research group, we did this reaction. We did this a long time ago because what we were trying to make, and I'll just kind of show you, we haven't done this in probably 10 years, but what we were trying to do was to take this acid called succinic acid, and we were trying to react this with NH3, and what would then happen is that we would basically convert one of the carboxylic acids into the ammonium carboxylate salt, and then when we heated this up, we would have closed the ring in order to make succinimide. Now, you may say, can't you just buy succinimide? And yes, you can buy succinimide, but what we were actually trying to do was we wanted to take our succinimide and treat it with lithium aluminum hydride, and this goes back to the last reaction or last lecture. We wanted to reduce the amide down to the amine, and this is called pyrrolidine. If there's 2 double bonds here, that's pyrrole, and how many times have we talked about whether pyrrole is aromatic or not? So what we wanted to do was to actually make pyrrole, and you may say, well, can't you buy pyrrole and you can buy it by the truckload? But what we were actually trying to do was to make a pyrrole that had an N15 nucleus instead of the normal isotope of nitrogen, which is N14. Now, nitrogen 15 turns out to be like, I don't know, it's a very small percentage of nitrogen 14. And I'll just say it's a small percentage. It may be that, but it's very small. It's probably less than 1%. And our issue was that we were trying to make 100% or as high as percentage of N15 as we could. Now what happens is people actually will separate the N14 ammonia from N15 ammonia. So it's very easy to do that. It's easy to do it. The problem is there's not a lot of nitrogen 15 isotope, and so what they will do is they'll sell you actually N15 ammonia that you can buy in a gas in a big round bottom flask. And so what we were actually doing was we were reacting the N15 gas with the succinimide and to make this ammonium salt. And then we heated this up using a round bottom flask with like a torch to heat this reaction up to basically form the succinimide, and then did the lithium aluminum hydride reduction to give us an N15 labeled pyrrolidine that we were using in some NMR studies. And there are other people. Another guy I found out later on was using N15 labeled ammonium chloride to do this reaction. But we actually went through and did the reaction. We never published it because all we did was verify another group's results and had some pretty serious limitations on how much we could use it. But my first master's student was actually the synthesis of this and using it in NMR studies. So we did go back to this really old decomposition reaction, but when we tried to heat the round bottom on a hot plate, we ended up not getting it hot enough. So we had to go back to like the 1920s conditions, which was to just basically heat it with a Bunsen burner as hot as it could get. So it is a useful reaction and it does work. And we actually used it later on. Another student of mine, another master's student, used it to actually take, and we'll talk about this reaction, but what was she doing? She was actually taking, she started with the succinimide instead of the succinic acid and reacted the succinic, this is called succinic anhydride, with the ammonia gas to basically make the pyrrolidine again. But then she also did a variation on this where she took the 6-membered ring and reacted this with the N15 labeled ammonia to make that 6-membered ring with the nitrogen, which is a different molecule altogether. Okay, so enough sidetracking. Lithium aluminum hydride reduction of carboxylic acid. So another reaction of a carboxylic acid that we've seen. Take a carboxylic acid, react it with H- that's coming from lithium aluminum hydride. We know the first step in this mechanism is that the hydride deprotonates the carboxylic acid to make the carboxylate. The second equivalent of H- comes in, adds to the carbonyl. And when it adds to the carbonyl, it forms our O-, our H, and our other O-, which looks like a hydrate without OHs. Now, when I talked about the mechanism of this reaction before, I said there was sort of a magic step that I didn't quite understand. I now understand it. Here's what happens in this reaction. The magic step isn't magic. Lithium aluminum hydride, this aluminum hydride molecule can actually give up a number of hydrogens. And so here's what happens. what happens is that we basically, this step leaves you with well, there's more than one molecule of lithium aluminum hydride. So after these hydrides leave, we have to put our counterions in. And here are our counterions. Our counterions look like this. We have an AlH2 here that has a +1 charge, and the lithium plus is the counterion for this oxygen. And what happens is that the electrons move like this. This pair of electrons moves here, and then if we think about this O-, aluminum, let's say I write this structure like this with a bond between the aluminum and the oxygen, then what will happen is that the O- moves here, and the oxygen then gives up its pair of electrons to that aluminum. So what we end up doing is we end up forming, now this oxygen does not actually form a double bond. Instead, what we end up with is we end up reforming the carbonyl with our aldehyde. But then the key step is we end up with a lithium plus on an O- that's now attached to an AlH2. And so this ionic species then, this actually makes a good leaving group, because then I form an aluminum with an O- on it that has a counterion of Li+. Then, of course, our other H- comes in, attacks the aldehyde, and we end up now with the alkoxide ion, and at that point we're stuck. After the reaction then is over, we add our H plus H2O to this, and that's where we get our CH2OH. We get our primary alcohol. So actually, this step is not actually all that magical, and you may say, yeah, but really, this whole thing is going to actually leave as a good leaving group? Well, yes, because when you talk about the molecule or the compound alumina, we used alumina in lab first semester. Alumina is aluminum oxide. So aluminum oxide is something along the lines of, Al2O3. But the key thing is aluminum has a great affinity for oxygen. So once that oxygen attaches to the alumina, it very easily will come off, and this bond is going to be very difficult to break. So what would happen is that these other H- would undergo reaction, and in the end we'd end up with an aluminum oxide ion as part of this reaction. So there is no magic to this step. We just have to include the counterions that we really don't ever talk about in this class. All right, acid chloride reduction to aldehydes. So our acid chloride reduction to aldehydes means that I need to use what? I need to use a carboxylic acid, and I need to reduce it. Am I going to reduce it with lithium aluminum hydride to get an aldehyde? No. If I use lithium aluminum hydride, as this was shown on the last slide, I'm going to make a primary alcohol. So I need to tone down the lithium aluminum hydride. So what did we use last time? Well, we could say, okay, I'm going to use lithium aluminum hydride, but I'm only going to include one H, and then maybe I'll put a couple of tertiary butoxide ions in here. So what I really have now is I've got the lithium plus on an aluminum, well, not attached to an aluminum, but I've got a lithium plus where the aluminum is now attached to 3 tertiary butoxide . and one lonely hydrogen. So now the aluminum only has one hydrogen to donate. And so in this reaction, what I would end up doing is I would end up not reacting the carboxylic acid because the carboxylic acid is going to be deprotonated by that H-. Instead, what I'm going to say is, okay, let's react the aluminum acid chloride with this. That one lonely H- is going to come in, add to the carbonyl. I'm going to end up with my O-, now with my H and my Cl. This pair of electrons comes back down here. What happens next? The Cl- leaves, so we end up with minus Cl, and we end up forming the aldehyde. And since this reagent now has a lot less reactive hydride, we stop at the aldehyde. So this will not work, so instead what I need to do is to use SOCl2 to convert acid to chloride and then reduce it with in essence, a deactivated lithium aluminum hydride. Okay, and this part of the mechanism, this part of the mechanism right here, takes us back to carboxylic acid derivatives reacting with strong nucleophiles, in this case acid chlorides. Conversion of carboxylic acids to ketones. A review. That's interesting. So I want to take a carboxylic acid. I want to start with a ketone. No, I don't. I want to start with a carboxylic acid. And then I want to convert it to a ketone. What should I use? Oh wait, this is review. You should know the answer to that question. Oh no, now I got to go back to the beginning and figure out how many of these reactions did I give you before. Again, stop swearing at the computer. What happened? Guess what? This is now online quiz question number 10. What reagent would I use to accomplish this transformation? How do I convert carboxylic acids to ketones? Okay. Acid chlorides, synthesis and reactions. I sense there could be a word here. Review. Good, because I'm running out of time if I'm going to keep this under an hour. So, acid chloride. How do we make a carboxylic acid into a carboxylic acid chloride? Question 11 on your online quiz. What reactions do we know about with acid chlorides? Oh my, I sense more reactions coming. How do I convert an acid chloride to an ester? What should I use? How do I convert an acid chloride to an amide? Number 13. Oh, this could go on all day. What should I react an acid chloride with to give me, I love this one, a ketone? Any other reactions that we should know about? No. Now I'm up to 14 questions. I won't even have to ask you any other questions on your online quiz. But I do want to talk about this. This will be the end. And then we will kind of move on in the next lecture. Carboxylic acid derivative. Carboxylic acid derivatives are called carboxylic acid derivative because they undergo hydrolysis to give carboxylic acids. And I'm going to talk just briefly about the mechanism of carboxylic acid hydrolysis of acid chlorides, but in general, the reason that a carboxylic acid derivative is called a derivative is because it undergoes hydrolysis to give a carboxylic acid. Now, what is hydrolysis? Hydrolysis literally translated is cleavage of water, cleavage by water. So hydrolysis can occur with H plus H2O as conditions. It can also occur with hydroxide and water. So you can get base hydrolysis or acidic hydrolysis. Every single one of the carboxylic acid derivatives that, if I go all the way back to the beginning here, every single one of these will give a carboxylic acid when they are hydrolyzed. Acid chloride, acid anhydride, the esters, and the amides. And we're going to talk about these mechanisms in the next lectures. But I want to talk about the acid chloride hydrolysis just to give you sort of those mechanisms. So in this particular case, our carboxylic acid derivative undergoes hydrolysis to give you the carboxylic acid. Now, there is one other compound that doesn't fit the C double bond O to the Y, and that is a nitrile. Nitrile also undergoes hydrolysis to give a carboxylic acid as well. And so nitrile is technically considered a carboxylic acid derivative, even though it doesn't fit the carboxylic acid derivative general formula. Oh, and by the way, this reagent, that might be on one of the online quiz or one of the online quiz answers, but I digress. What would the mechanism be for reacting just flat out water with acid chloride? And I'm going to take away those equilibrium arrows because they're not. This is a 100% reaction. Could you write this mechanism out? Well, it turns out that the carbonyl here is particularly unstable because an acid chloride, you've got electrons being pulled to the chlorine, electrons being pulled to the oxygen. That makes this carbon much more delta positive. So actually water doesn't need acid to help. Water will directly attack the carbonyl, and so we'll end up with this. Now there's a couple of mechanisms you can think about here. You could say, oh, the proton transfer is here to there, but that's not helpful. I mean, it could be helpful, I suppose. But if it does, then you would end up with this. But now what happens is pair of electrons moves here. Chloride gets kicked off. We end up losing HCl. And we would very easily end up with our carbonyl and our alcohol. So acid chlorides react with water very efficiently to form HCl and the carboxylic acid. You can also do base hydrolysis just to give you a feel of what those mechanisms are going to look like. So if I take my acid chloride and I react it with my hydroxide, it's going to come in, add to the carbonyl. I'm going to end up with an O- up here, a Cl, an OH. Now this pair of electrons comes down. which is a better leaving group, chloride or hydroxide? If you said chloride, you're correct. So now I'm going to actually lose chloride, and I would end up forming my carboxylic acid. But here's one little key with this reaction. When you do base hydrolysis, that means you've got extra hydroxide present. So it would actually deprotonate so that you would end up with the carboxylate salt. And so if you do base hydrolysis of an acid chloride, you need to do a then H plus step to get you back to the carboxylic acid. So we're going to talk about more of these mechanisms of the acid chlorides. We'll talk about that in the next lecture, as well as then going through the reactions of the carboxylic acid derivatives in order to make all of the different derivatives and go through their reactions. All right, so your online quiz for this lecture is going to be to give me the reagents that you would use for the reactions number 1 through number 14. And you can either give me the reagents or you can write their names out, either one.